idea on what gonna happen in AC circuit analysis, especially for nodal and mesh analysis. Um, the way we analyze our circuit using mesh, nodal and mesh. And I also put some 4 examples um, extracted from your textbook. Here is the 4 example. Example 10.1 up until example 10.4. And I also posted a class activity, i.e. homeworks for you guys, in order for you to get familiar with the analysis using mesh and also nodes for AC circuit. If you, I think it's a good idea for you guys to have a look at the videos that I included inside week 10. I think I have 2 videos. It's very good video for you guys to learn or to strengthen your knowledge on nodal and also mesh analysis, especially for AC circuit. And if I check our homework submission, the last time we have homework submission is in week 9, where I think still some of you guys didn't submit your homework. So hope you submit your homework by this week. And I come across to previous homework that I asked you to do, which is in week 7. I think some of you guys still didn't submit. Is Akil over here? Ame Akil, please submit your class activity. I think week 7. Week 5 is okay, but week 7, it's I think it's been pending for quite some time. All right. Okay, we proceed to the one that I mentioned last week. It's regarding assignment 1. Okay, assignment 1, I still haven't posted this information or this slide in e-learning. Maybe later on, because I would like to finalize the wording over here, how you should follow the instruction of assignment number 1. Okay, for assignment, basically it's we have 2 assignments. This is the first assignment where you need to use multisim. In your second assignment, also you need to use multisim in order to finish your work, the task. All right. For assignment, basically it falls in. If you look at our course information, it falls in course learning number 3, where in this course learning number 3, the one that we try to assess is the ability of teamwork, and also you need to proceed or to conduct with the assignment. You need to have what we call it, independent learning, in terms of finding the sources and also try to work around how to solve your circuit using this multisim software. I've already posted some of the example. I think multisim software is quite easy to use, and the thing that you need to learn about is about how to connect your meters. For example, how to connect voltmeter, how to connect ammeter in your circuit in order for you guys to analyze what is the current or the voltage across that element. Okay, for the instruction, you will be divided into group of three, into three groups, or not three groups. Basically, it's a group of three. Each group consists of three students, where you need to solve the circuit given using multisim, and also need to calculate the your answer in order for you to compare based on calculation as well as based on the simulation answer. And at the end, you need to prepare a report. This is a group report, and you need to state the work distribution. For example, student number one solving question number one, student number two, question number two, for example. So you need to state the work distribution of your group members. And for the submission, only group leader will submit the assignment, and the link to submit this, I think I will prepare it in through e-learning. So you will submit your report through e-learning, and one thing that which is very crucial over here is about the evaluation. The peer evaluation means that you need to evaluate your teammates, your group member, in order to gain marks. So in general, the marks for this assignment is around is about 10% or 10 marks, where 5% or 5 marks will be from me. I will evaluate your report and your simulations, and another 5 marks is based on peer evaluation. So you need to evaluate your teammates. The evaluation link, or how do you gonna evaluate your teammates is the link will be given to you later on. I think I will design a Google form, and then you need to try to evaluate your teammates based according to the rubric inside the Google form. All right, in terms of grouping, I've prepared the group list. Here we have 6 group. Unfortunately, for the last group, which is group number 6, Abu Bakar and Izaidi, only you have 2 of students inside group number 6, meaning that you need to have extra works lah in terms of finishing up the assignments. This is something which is I've already explained just now. Okay, the circuit will be looks like this. For example, question number 1 here. I think I have about 3 questions. So maybe one student will take 1 question. You need to simulate and then calculate manually. And at the end of at the end of your answer, you also need to compare your finding. Compare the answer given by simulation as well as answer given by manual calculation. And maybe what you need to do, not maybe, you need to describe whether, okay, your simulation giving you the same answer with your manual calculation, or a manual calculation also give the same answer as simulation. If not, maybe you should state the reason why your answer is a bit different based on simulation results as well as um, calculated manually. So you need to describe your finding. Please, just maybe about one sentence, a statement. Why? If both answer is the same, then it is easy. Maybe you can say, okay, both simulation result and manual calculation give the same answer. Uh, Maybe that should be enough. Okay, we have 3 questions, and please make sure during the evaluation, if your team member or your group member did not support you to in order to finish up this assignment, please assess your team member fairly. If he give a full support, and maybe you can give high marks to him or to her. If not that much contribution, maybe you can consider giving fair marks to him or to her. All right, that's for assignment. Maybe later on I will post it in e-learning, and you can download this file later on. All right, we move back to our main agenda today, which is the content for today's lecture is about analyzing a C circuit using mesh as well as node analysis. I believe the strategy to analyze a circuit using nodal or mesh we have been discussed this part in DC circuit before semester break, and we will apply that knowledge here in to solve AC circuit. All right, I think I've explained this one. Nodal and mesh analysis will be discussed. Yes. All right. The difference between DC circuit analysis and AC circuit analysis is that in AC circuit analysis, it involves frequency. So in order for us to analyze the circuit in frequency domain, or in I would say a lot simpler strategy to analyze AC circuit, we should make use of the frequency and transform the circuit from phasor from time domain into a phasor or frequency domain. So in order for us to transform the circuit is still the same. It's not saying that if we try to transform from time domain to frequency domain, the circuit will be modified, or it's the arrangement of the component will be different. The arrangement of the component is still the same. However, the value of each passive component, for example, capacitor and inductor, will be converted into a frequency domain quantities. So here, the word transform the circuit, not meaning that we try to modify the arrangement of the circuit. What we try to do is we try to modify a bit the quantities of the elements inside the circuit. The arrangement will keep as what we have seen in time domain connection. And from that transformation, or from that kind of after we convert from time domain into a frequency domain, we can easily solve any the problem inside a circuit using any circuit analysis technique. Or maybe you try to use mesh, nodal, or maybe superposition, source transformation. Any circuit analysis technique can be applied after you transform your circuit into a frequency domain circuit. And the third one is transform back to time domain. It doesn't matter whether you would try to transform it back or not. However, you should follow whatever stated in the question. If the question asks about, for example, current flowing through that branch, current flowing through branch number 1, please write it in time domain equation. So that's the way, that's when you try to transform back your answer into the time domain quantities. If not, maybe you can leave your answer, or you can leave the values in frequency domain, because it's understood that the problem is solved, only that it is represented in a frequency domain values. Okay, as we know, as we learn in DC circuit, we know that for nodal analysis, we try to apply KCL. Here it says it is possible to use KCL to analyze a circuit in frequency domain. Yes, of course. First, for AC circuit analysis, we need to transform our circuit, or the values of the component inside the AC circuit in frequency domain. So from there, you can apply, for instance, for this analysis, nodal analysis, you can apply KCL to analyze your circuit. I think I mentioned about the second point over here. The first step is to convert time domain into frequency domain by calculating the impedances of the circuit elements at the frequency, at the operating frequency. So operating frequency normally will be given in the question, or you can have a look at the supply or the sources inside the circuit. For example, if the circuit have voltage source, have a look at the frequency of the voltage source. And if you have a current source as well as voltage source, have a look at those two sources frequencies. Okay, note that the AC source appears as DC source with their value expressed as their amplitude. This is something which is related to how we draw the circuit after we transform it into a frequency domain. So sometimes to make our calculation easier, or sometimes if, to make the circuit is graphically easy to understand, we try to draw back to draw our sources from the AC sources in terms of DC sources. For example, if you have like earlier, maybe draw it here. Okay, for example, if first we have something which is look like this. Okay, the first one, maybe this is what 5 millihenry. Okay, this is something maybe 10 ohm. And our voltage here is written in sinusoid form. For example, this is V of t 10 maybe I should write it down here. 10 sine 60 t plus 10, for example. Okay, what you need to do, you need to transform, in order to solve using nodal analysis. First, you need to transform your circuit in frequency domain, and in order just in order to make it graphically easy to understand, you can also draw your voltage source or your current source. For example, this is a voltage source like this. And remember that this is for Z. I usually use box symbol, and also for reactance, I usually use box symbol here. So now, for the voltage, you can write like this, and with the angle of 10 degrees. And here is 10 ohm. And for your XL, it will be coming from 60 times 5 milli. And you should get your answer in terms of ohms over here. So later on, you can combine these two elements, 10 and also basically, let's say if I calculated this one and it gives me like what call it? Maybe I put it in C, maybe not C, cannot see. C is a bit, maybe I put it as XL ohm, XL over here. And my total impedance, Z, is given by 10. Remember, this is an inductor, so it's going to be plus J XL, whatever value of XL. And both, since both are in unit of ohm, so you're going to have impedance Z in unit of ohm as well. So this is what happened at early stage of circuit analysis for AC circuit. You need to transform from time domain, this is considered time domain, and this is your frequency domain. And from here, if you like to calculate what is the current over here, you can simply apply Ohm's law. V equals to Iz and I equals to V over Z in order for you to calculate what is the value of current. So that's for the first one. And if we continue here, I think we already discussed this part. Impedance will be expressed as a complex number. If you look at the circuit I draw just now, yes, of course, it's expressed in complex number because we have inductor component over there, where inductor will be treated as reactance in frequency domain. And sources, we will represent it in amplitude and also phase. You see over here, we have the amplitude of our source, voltage source, and also the phase or the angle of our voltage source. And okay, we can proceed with nodal analysis where we can apply KCL. So this figure or this circuit is not we can solve that circuit not using nodal, but if we have a circuit which requires nodal analysis in order for us to analyze it, so we can proceed with the steps for nodal analysis. Um, if you look at our previous lesson, if we have like a voltage in between two nodes, sorry, if you have voltage source in between two nodes, so we need to treat it as a super nodes. So super node also can be applied in AC circuit. Um, and as usual, what we need to do, we need to make our circuit or transform our circuit in frequency domain. If you look at here, we have negative J3, we have negative J3 over here, we have J6, and what else? Oh, okay, that's it. And also, if you look at the current supply and also voltage supply, all been converted into frequency domain values. For voltage, we see for current, we see that we have the amplitude as well as the angle over here, the phase, and same goes to voltage. We have the amplitude as well as the angle of the voltage source. And for the passive component, for example, an inductor and also capacitor being converted into its reactance value. So here we have C or being converted into XC, and basically XC is the value. If you look at here, XC is only this value 3 is XC. The whole thing is considered, the whole here negative J 3 ohm is considered as negative J XC. And same goes to inductor. If you look here, we have J6. Basically, this is JXL. And if we noted in the circuit, we have we have a voltage source in between two nodes. Means that we need to use super node strategy or super node analysis to analyze this kind of circuit. All right. For mesh analysis, okay, since we apply KCL for node analysis, for mesh analysis, what we need to do, we need to apply KVL. So this is the difference between node and mesh analysis. If you want to know, you want to know the details of solving a circuit using mesh analysis, maybe you can have a look at our previous lesson before the semester break. And the rules applied here is always the same, where we try to convert first into a frequency domain, and later on we try to apply KVL. And if we have like super mesh, for example, in this circuit we have super mesh, we have current in between two meshes, so we need to apply super mesh analysis to analyze our circuit. So that's about today's lesson. We have the main essence over here, or the important point here, is that first thing you need to convert from time domain into a frequency domain. If you are given a circuit in a frequency domain, means that your calculation or you can skip that step. You can straight go to analyze your circuit using either mesh or either node according to the question given, instruction given in the question. All right. Any questions so far?
Nope.
Okay, can follow, yeah. All right, we look at example 10.1. Okay, in this example, uh, if you look at the circuit itself, components over here, maybe we have capacitor and also inductor here, and finally we have inductor over here. Okay. All the values of these three elements were given according to their time domain value. For example, for capacitor, we have 0.1 farad. Inductor here, number one, we have 1 Henry, and another one is 0.5 Henry. So you should also note that your voltage source over here, okay, is given in a time domain value. So how do you know? Because we have this kind of sinusoid um, equation. From there, we know that, okay, this is in time domain. And if you look at the component itself, also still not being converted into a frequency domain value. And according to the voltage source given in the question, you see here we have the amplitude is 20 and cos 40. 4 over here is basically our omega. And this omega will be used in order for us to get or to transform these three components into its frequency domain value. Okay, let's see the solution. Basically, uh, the solution is available in your textbook, as well as I've already put it in our e-learning portal. You can have a look later on. But here I just would like to discuss important points in order for you to get better understanding what's going on in the solution. Okay, I think this one is wrongly um, noted or denoted wrongly. Should be omega over here, but since it use ohm, so it will apply ohms throughout the solution. It's okay. All right, now the first one, in order for us to solve this problem, okay, before that, the the question asks about Ix, where Ix is current flowing through this um, 0.1 farad capacitor. And you cannot solve um, the circuit using, uh, for example, here asks about nodal analysis. You cannot solve it using nodal analysis unless you convert this into a frequency domain circuit. First, you need to convert or transform this kind of circuit into a frequency domain circuit. And if you look at the frequency equivalent circuit, frequency domain equivalent circuit, or frequency domain circuit, the arrangement of uh, components is still the same. We didn't change the arrangement of the connection. What had been changed over here is the value of capacitor and inductor, where capacitor and inductor will be transformed into its reactance value. And this capacitor, for example, is given by negative JXC, and this one given by JXL, and this inductor is given by JXL. Maybe this one is XL number 1, this is XL number 2. So the way we calculate the value of this reactance is by using this calculation. And for XL, it is given by XL is given by omega times L. And for XC is given by 1 over omega times C. And you would wondering why this one don't have a negative, but here we have negative. It is happen because this negative is due to 1 over G over here. So we try to write it in a numerator form, so it will become negative J XC. And XC is given by only by this equation. And for XL, as I mentioned earlier, it is given by this omega L. And L is quite, the value of L and the value of C is quite straightforward from the circuit. However, for omega, you need to identify that this value or 4 over here is basically telling us the value of our omega. And sometimes frequency value of this AC circuit is embedded into omega value, where here we know that omega can also be written as 2 pi f. Okay, if you like to if the question asks about the frequency, just rearrange this formula. F equals to omega over 2 pi, and you will get your frequency value. But you don't have to calculate frequency unless it asks the question asks you to calculate the frequency. Or if you look at the way to calculate XL and also XC, you can straight away apply value of omega in order for you to calculate XL or XC. Now, the first step is finished. We try to convert from or to transform our time domain circuit into a frequency domain circuit. And again, I would remind you guys that the conversion from time domain to frequency domain does not change the arrangement of the circuit connection. The only changes in the circuit is the value over here. Value will be given by its reactance value as well as its resistance value over here for resistor. Okay, and we can proceed to apply our KCL in order for to analyze our circuit using nodal analysis. And if you look at the rest of the analysis, we try to apply KCL here at node 1. If you look at node 1, we have current here. This is IX. Maybe this is I1. I label it as I1 and this is I2. Okay. Looking at the original question, current I1 and current I2 haven't been labeled yet. And you can label it by yourself. And in this solution, the I1 and I2 is labeled based on this direction. If you would like to change the direction, for example, if you would like to change it towards that direction, so it also can. You can also do that, but remember that you need to keep this direction throughout your analysis. And if you change, if you draw the direction like this, i.e. in the opposite direction, you need also to consider the equation of Kirchhoff current law at this point. So it's not going to seem like what you've seen in this solution. So in this solution, it is based on the direction for I1 is pointing towards your right hand side, and for I2 as well as I2 towards the right hand side, and for IX is pointing downwards. So be careful with that. And although you can do this, but make sure you know how to you be particular with the current direction throughout your analysis. Okay, based on this KCL at node number 1, you know that I1 is the current coming in should be equals to the summation of I2 and IX. So here, the equation that you found over here is based on this basic equation. So I1 given by 20 minus V1 divided by 10. So this is 20 minus V1 divided by 10. And I2, current over here, is given by V1 minus V2 divided by J4. And for IX, current going downwards, is given by V1 divided by this negative 2.5 ohm. So this equation, this one is basically based on this basic node equation, or current coming in and out of node number 1. And the difficult part in order to analyze AC circuit is that in AC circuit, it involves a complex number. So you need to be particular with your calculation. Okay, here we have imaginary part of our complex number. So be careful with that. I don't want to get into details on this, because this is something which is involving mathematics, where you can always revise it later. But if you look at the strategy that the solution over here, from the solution over here, we try to eliminate the denominator part. For example, to convert from the first step into the second step, you should eliminate the denominator part. For example, here, what I try to do is that if we have 20 minus V1, okay, should be multiplied with negative J 2.5 times J4. Equals to V1 multiplied by 10 plus, not plus, multiply with what else? J4 plus, we have V1 minus V2 multiplied by 10 and negative G 2.5. Okay. How I come up with this kind of equation, it is by multiplying both sides with 10, negative 3, 2.5, and T4. Multiply. So maybe I should put some comment over here. Multiply. Okay, multiply both sides with this one. If you multiply both sides with 10, negative j 2.5, and also j4, you will eliminate the denominator of this first equation. So from there, you need to multiply that lah. I mean, you need to expand your equation. From there, you need to expand, and at the end, you will come across with this equation. So it's the tedious part is involving because the equation you try to handle equation involving a complex number. So I believe that one is the part where it comes very you need to be particular with your calculation. Other than that, it's a basic nodal or mesh analysis. Okay, with the constraint of time during your exam, so I think this could be a crucial point lah. I mean, you need to do more practice in order for you to get familiar with the calculations. If you don't practice, means it's not gonna, you think it's quite hard. All right, that is that note number one. At note number two, if we look at note number two, okay, I draw it here first. Okay. I have I2 previously over here. Maybe this is current, the new current that I got the notation. Maybe this one is already given in the question. It's 2ix, I believe. 2ix, yeah. Okay. And if you look at this equation, basically coming from this definition. So here we have current coming in is I2 and also 2ix. Current out is I3. Based on this basic equation, you can expand it into this kind of, or this new equation involving voltage and also Ix we defined earlier, defined in question earlier. And the rest, I think it's involved mathematics. You need to have a look at that, and the way we solve it. First, if you look at the equation, it involves two unknown variables. We have in terms of current and also in terms of voltages. And we know that to solve using node analysis, we need to represent our equation, node equation, in the form or with respect to voltages. So here we have Ix, where we need to get the definition of Ix in terms of voltage. According to the according to the circuit over here, Ix is the current flowing through this capacitor. And current over here is given by V1 divided by negative J2.5. So that's why here Ix is substituted into this equation. After you substitute this equation, you see here we have denominators, and just by simplifying, it says simplify or simple. It's not that simple, because what we try to do over here, we try to eliminate this denominator part, this three denominator part. And the way we eliminate this denominator part is by using the way that I showed just now. We multiply both sides with, for instance, in this case, we multiply both sides with negative J2.5, J4, and also J2. Later on, you need to expand your equation, and at the end, you will get into this equation where we have 11 V1 plus 15 V2. From here to here, although it says like a simple strategy, that is not, it is not very simple. It involves a lot of calculation, mathematics, where you need to eliminate the denominator and later on do some, you need to expand your the equation to reach this stage. All right, same goes here lah. Okay, now we have two equations. Okay, maybe I try to change the color. Now we have two equations with two unknown variables. Equation 10.1.2 and 10.1.1. Here we have V1 and V2. Same goes to here, we have V1 as well as V2. And you can solve the unknown variable over here, V1 as well as V2, using any strategy that you prefer. In this solution, we use Cramer rule, I believe, because we have determinants over here. But for me, I would prefer maybe substitution, where I substitute V1, for example here, we have 11 V1 plus 15 V2 equals to 0. And maybe I put it this way, 11 or V1 equals to negative 15 V2 divided by 11. And I would substitute this V1 into this equation. Maybe that's the easiest way if you try to avoid this matrix form or try to find the determinant and so on. One more option, maybe you still need to put it in matrix form and try to get inverse matrix of this. You can also use inverse matrix of this matrix and multiply with this 2 by 1 matrix. That also can. But in this solution, it used Cramer rule over here. Here is Cramer rule in order to calculate V1 and also V2. Maybe later on, you should have a look at this in details, because it is just mathematics calculation involved over here. All right, we go back to the question where we try to find the current Ix. If you look at Ix over here, finding Ix. Ix over here is the current flowing through this capacitor. So this current can be found if we solve this equation. Ix equals to V1 divided by negative J 2.5. And since we solve V1 and V2 values, Ix can be easily being calculated, and this is the answer of Ix. And although in the question it doesn't mention about the time domain, whether you should represent your answer in time domain or in frequency domain. But since you look at the question given in a time domain value, and the current here is sorry for that. Current Ix here is not written in capital value. Maybe capital value, small, sorry, capital letters, not capital letters, cannot be accepted. Maybe if you look at the question, or the original question is given in time domain representation, meaning that the current that you need to calculate also need to be transformed back into its time domain value. And in time domain value, if you try to write down in time domain, current in time domain, you should take this value as its amplitude, and also this value as the current phase angle. And the amplitude can be written here, and the angle can be written at the back at the end of the equation. And if you notice that the form here, we use cosine and omega still kept as the same value we've seen earlier. So that's how we transform from frequency domain value into a time domain value. But for me, I think the difficult part is not here. The difficult part to analyze the circuit is here. This part, of course, and until you find into this part. These 4 parts very crucial. That is for note number 1 and note number 2. For note number 1, I think conversion from this equation into this kind of form is very crucial, because you tend to do mistakes over here. If you not particular with the complex or the complex number multiplication or division or addition, subtraction, you tend to do mistakes converting from this equation into this equation. If you got it right and your answer is, I think the rest will be very simple. Okay, any questions so far?
No.
Okay, all right, that's for example 10.1. For example 10.2, I think you can revise it by your own, because I uh, also put the solution for example 10.2 in e-learning. And what I need to what call it, highlight over here is like, if you look at the circuit and try to solve it using node analysis, you need to be aware that we have a voltage source in between two nodes. So here, the circuit must be solved using supernode analysis. Okay, I have the solution here, but I think I will leave you guys to do some revision on how to solve it. It's quite short over here, and please do some revision for this example later on. Maybe you will wondering why, how do we get this part? So this is the explanation on how do we get that part. But I need you guys to work it out by your own so that you will understand it better. All right, we move into our next example. Okay. Okay. All right. Example 10.4. I need to change this figure back because this is not for example 10.4. But anyway, we are in example 10.3. If you look at this example, we need to determine current IO, okay, using mesh analysis. Okay, and according to the question or to the circuit, we have three meshes. The first one is down here. Second one is over here at the right hand side, involving encircling the 20 with angle 90 degrees voltage source. And the third mesh is encircling the 5 with the angle of 0 degrees ampere current source. So we have three meshes over here. The first one here, mesh number 1, mesh number 2, and mesh number 3. And if you look at the current direction in the circuit, it's already been given to you. So you should follow the current direction given in the question. Right. According to the figures as well, if you try to find what is the current of IO, you need to be aware that IO, okay, this is something, a rough idea about IO. IO can be found if you know what is the value of I2. And since the direction of I2 and IO is in opposite direction, means that IO is basically negative I2. And if you know what is I2, then IO is solved. Just put it a negative value over here. This is because you see here I2 is going this way, I out or IO is going in the opposite direction of I2. Okay, about the solution. Right now, the you can find the solution as well in your textbook, page 415, I believe. Right. Looking at the solution here, we need to apply mesh analysis in order for us to calculate what is the value of IO. And to use mesh analysis, the first thing that you need to understand is that you need to work out the KVL around the meshes. And in this case, we have three meshes, as I noted earlier. We have I1, I2, and also I3. So we try to work out these three meshes one by one. Okay. The first one, we have a look at mesh number one. Okay. Mesh number one, according to this circuit, we have inductor, capacitor, and resistor. And all is given in its frequency domain value, where this one is J10, this one is negative J2, and this one is 8 ohm. Every components inside here already been transformed into a frequency domain. The thing that you need to do in order to analyze using mesh is to assign the polarity of voltage drop across these three elements. Since you know that the current is flowing this way, means that this should be a positive, it should be negative, it should be a positive, negative, positive, and negative. That is the polarity of the voltage drop across these three elements. And sorry, in order for us to calculate the voltage drop, you know that voltage is given by V equals to IZ, I times Z. Okay, IZ here. And looking at the voltage drop, first we need to know what is the current flowing through this 8 ohm. And we also need to know what is the current flowing through this J10 ohm, and as well as this negative J2 ohm. What is the current flowing through here? And it is straightforward for us to identify that the current flowing through this 8 ohm resistor is I1. However, the current flowing through this J10 current over here cannot be labeled as I1. Maybe I label it as IA. And current flowing through here this, oh, sorry. Okay. It's not I1 as well. It's a combination of two currents. And I don't know what is the combination yet, but at the moment I put it as IB. And looking at the equation that you see over here, basically it is coming from this basic equation. If you go around the loop for loop number one, mesh number one, if I start over here, I would see that, okay, I have positive 8I1 times I1 plus IA times J10 plus, again, plus over here, IB times negative J2, and closing the loop equals to 0. So we will start from this basic equation, okay, for the first mesh. And now I try to find what is the definition of IA And what is IB? Because I know IA and IB is not I1. It's the combination of two currents. Therefore, for IA, I'll be looking at this point here, looking at here, okay, where at that point, I have current I1 coming in, I3 going out from that point, and IA flowing in that direction, because I label this one as positive, of course lah, because current coming in, we will label it as a positive polarity over here. And from here, I can write down my IA equation, which is given by I1 minus I3. IA over here is given by I1 minus I3. This is from Kirchhoff current law, where current coming in, sum of I in should be equal, no, this is not I1, yeah, sum of I out. We solve IA and put IA in that equation. And later on for IB, I know that IB is not I1 because IB is current over here. And for current over here, I can either use this connection or this point, or or this connection, this point, either using this point or this point. But if you look at this point, it involves IE as well as it involves I3, not I3. This is also not I3. This is combination of current I3 and as well as I2. So it's very complicated over here. What I try to select is that I would like to select a node which is clearly indicated that that is the current coming in and coming out from that node. So I think this one is not suitable, and this is more suitable, because at this point or at this node, I have, like here, this is the junction, I have IB that I want, and I1 over here flowing out from that node, and I2 coming into the node, because this is definitely I2 and this is definitely I1. So this is a certain current, or the definite current coming in and out from within that node. So using this point or at this node, I can write down my IB. IB is given as I1 minus I2 in this case. And if you ask about how do we get this equation, it is coming from KCL definition, where sum of I in equals to sum of I out. All right, now we know what is IB, and we substitute IB into this equation. And if you expand this equation, it will give you this final equation. So it is not that easy to get this equation. Okay. It's not that easy to get this equation because we have a few steps before we come across with this simple equation. And if you look at here, it does not involve any denominator part, so our calculation will be a lot more easier, or a bit easier compared to what we've seen in nodal analysis, because we don't have to multiply both sides with values that will eliminate the denominator part. All right. When you try to expand this one, finally you get into this equation. That is equation number 1. And equation number 2 is coming from mesh number 2. If you look at mesh number 2, if the current is flowing in that direction, okay, before that, I'll try to draw back mesh number 2. Mesh number 2 consists of resistor, voltage source, capacitor over here, and capacity up here. Okay, since the current is flowing in that direction, I'll try to label my voltage drop is to be this in this direction. In this polarity. Okay, and I try to, maybe I use different color, like right, and I try to assess what is the current coming into this node. If you look here, it's definitely I2, and current flowing through this element is not I2. Maybe I put it as ID. And current flowing through this element is not also I2. Maybe I put it as IC. Okay. Why I put D here is ID. Why not I put IC? Later on I will explain. All right. If you look at this circuit, we have this 20 angle of 90. I can write down my equation as, for here, if I start from where, yeah? If I start from here, let's say I start from here, I have here. I have ID times negative T2 plus IC times also negative J2. Then I have plus 4 times I2 more here. Okay. Equals, sorry, not equals, it should be plus 20 with the angle of 90 degrees. Oh my goodness, 90 is not 90 degrees equals 0. Okay, I have this equation based on this loop where ID times J, this is negative J2, this is also negative J2. And I know that the only the only component that I2 is flowing through it is this 4 ohms resistor. If you look at here, this is definitely the current over here is definitely I2. However, the current flowing through this element, this negative J2, is not I2. Same goes to negative J2 at the top here is not I2. Here must be the combination of current, I don't know yet, and here also the combination of current, maybe I3 and I2. This one is maybe from based on I1 and also I2. Okay. Earlier, you know that the current is flowing in downwards direction is considered as IB. Okay, here, the definition over here. And if I want to know what is the current pointing upwards, where here current pointing upwards is labeled as ID. So I actually don't have to do calculation because I know ID is negative IB. And it is given by it's given by I2 minus I1 in this case. It is ID because we already determine what is IB, and we see that here the direction of ID is in the opposite direction of IB. So using that definition or using the one that we calculate, we determined earlier, we can know what is the value of ID, the equation of ID itself. Except that here we have IC. IC is current over here. Okay. IC, I have two options, whether to assess this point or maybe I can assess this point. And as I explained earlier, in order to assess the point at the middle over here is quite difficult because it involves current which is contain another current. So it's quite tricky to analyze the current over here. So what I'm trying to focus is that I focus at the point at the top over here. So point here is actually here. I draw it a bit bigger over here, where I know that the current coming into this node is the I3 and my current here IC, the one that I would like to find. And current at the right hand side or flowing out from that node is I2. So I have equation of IC given by I2 minus I3 over here based on this point or at this node. Using that definition, IC and ID, I will substitute my IC down here, ID also can be substituted over here, and at the end, from this basic equation, finally I will get into this final equation. Okay, it's not that easy, I know, but you need to start your calculation based on your based on the simple equation. We finish with mesh number 2 and we get into mesh number 3. I think mesh number 3 is quite easy because we have current definition inside mesh number 3. And that's why here you see that, change the color first. You see that for mesh number 3, I3 is given by 5 ampere, and basically you need to put it as 5 with the angle of 0. But If you don't do that, also can, because the calculation will be the same. Okay, maybe I delete this one and try to write down here I3 as equals to 5 with the angle of 0 degrees. You can write it like this, or you can write it with the angle information as well. But if you look at mathematical definition, if angle is 0, you can straightforward write it as 5. All right. Using this I3 definition, okay, using this I3 information or definition, you can call it anyway, using this value, substitute I3 in your first and second equation that you write before this earlier. And if you substitute I3, you will be eliminating this element, not eliminating like that, like substituting that element, and also substituting this element, and at the end you will end up with two equation involving only two unknown variable, which is I1 and I2, and the rest is based on your mathematics knowledge to solve two unknown variable. However, this the task is not as easy as you think, because it involves complex number. So in calculation involving complex number is it's a tedious work. You easily get do mistakes, or you easily get into an error in order to solve complex number. So be careful with that. And in this solution, we try to solve these two unknown variables using Cramer rule, or you can also use substitution, as I mentioned earlier, or you can also use inverse matrix in order for you to solve these two unknown variables. The rest, I think, you need to revise it back, how to solve these two unknown variables. The electrical parts, or the electronics knowledge, it's up until this part, I believe. The rest will be involving your mathematics knowledge. All right. We back into the question. The question asks about I/O, and we know that I/O is given by negative I2. Since solving these two unknown parameters, we also solve I2. So here, just take the negative value of I2 for us to solve what is the value of I/O. Then I think that's the one which is very important over here, is that you need to know how to apply mesh analysis. If you look at the solution that I show you just now, the mesh analysis strategy, we already discussed this one during the first half of our semester, during the DC circuit analysis. However, the difference applying that knowledge into this kind of situation is that this AC circuit involves complex number. So the complex number, it's not easy to be handled. So you tend to make mistake in your calculation. So please be careful with your calculation. But for The electrical part, I think it's very straightforward. It's very it's the strategy that we apply here is based on what we learned earlier in the first half of the semester. All right. If you look at my final example, this is example 10.4, but I really apologize. This is not the 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 figure that I would like to show to you. Maybe later on I will re-upload the correct version of the slide, but this is not the one that I would like to show to you because this is the same as example 10.3. Okay, for example 10.4, I also had uploaded in your e-learning portal. You can have a look at the e-learning portal to have a look at the example 10.4. And example 10.4, if I'm not mistaken, sorry for that. If you look, okay, this is the correct figure for example 10.4. If you look at example 10.4, we have like, I'm not gonna get into one by one, yeah. Maybe you can revise it by yourself. We have one mesh over here, another mesh over here, and in between these two meshes, we have this current source. Means that in this example, we need to apply super mesh. Okay. Here it also says that meshes 3 and 4 forms a super mesh due to the current source between the meshes. For mesh number 1, maybe says here, maybe mesh number 1, here is mesh number 2. Mesh number 1, mesh number 2, maybe this is mesh number 3, mesh number 4. Have a look at that. Okay. These two meshes will form a super mesh and start solving the circuit using mesh number 1 first, and later on get into the super mesh. All right, here is the complete solution. You can have a look. I think the solution over here tells us about how to solve your mesh analysis using method number 1. I think this one is manual calculation using Cramer rule, and this one is by using MATLAB. But I think MATLAB, you actually you need to get this equation right first, these two equations right first, and also I think that one, so that two equations right first. And if you don't get these two right, forget about MATLAB or forget about solving, whether using manual calculation or MATLAB calculation. All right, I think this example you can revise by your own in based on the textbook. And before you get into this 10.4 example 10.4, I strongly suggest you get into example 10.3 first. This is 10.4, sorry, 10.3. Please understand this one first. If you don't understand this circuit, forget about 10.4. Please understand how to solve this simple mesh analysis of AC circuit and build your knowledge or build your confidence in order to solve super mesh based on your knowledge of basic mesh analysis. So if you don't have a very good knowledge and have, sorry, if you don't have any like your basic is not strong, uh, it's quite hard to understand about super mesh or super node. So based on my suggestion, I think please revise back example 10.3 as well as example 10.1 over here, 10.1. So this is a basic um, nodal as well as mesh analysis for you to get familiar with um, complex number involving in our circuit calculation. Okay, any questions so far?
No, sir.
Is it okay or not okay?
It's okay, sir.
Okay. Uh, right. If you look at the content that we discussed today, yeah, if you look at the content that we discussed today, and you know that there are 3 steps, or maybe I would reduce it into 2 steps. That's very important. This one is crucially important. You need to transform your circuit from time domain into a frequency domain. If you don't know how to transform your circuit from time domain to frequency domain, start doing it now. And later on, if you try to get into the analysis using techniques or using circuit analysis method, you cannot get into that one unless you transform your circuit into frequency domain values. Later on, you after you convert into a frequency domain values, yes, later on you can solve it using any circuit technique that available. Today I'm presenting or I'm explaining about nodal and mesh. And you see that uh, in nodal and mesh analysis, the strategy that we apply to solve a circuit either using nodal or using mesh analysis, it's the same that we seen in DC circuit when we try to analyze DC circuit. Except that for AC circuit, the the calculation is a bit tricky. I mean, the it involves complex number, so you tend to make mistake when dealing with that kind of um, complex number stuff. So it involves real part, imaginary part, and how do we treat the imaginary part. When we try to multiply j and j, it will become -1. That is the thing that there are the things that you need to really particular with. So be careful with that because it is um, crucial for you guys to be like very details on your calculation because if you like wrongly multiply, for example, minus j times j, it should be like 1, right? But you put it as -1 and the whole calculation will be wrong later on. So that's very important for you to be particular with your calculation dealing with complex number. Uh, Apart from that, I think that's the other is like simultaneous equation and so on is something you have been come across. It's not like new to you. The new one or the new things that you will face in this analysis is that you need to deal with complex number. So remember that in AC circuit. But anyway, if you do a lot of exercise, not only given exercise, maybe other exercise available in the book. It's not that difficult because you train yourself to face this kind of um, calculation involving complex number. So anyway, that's some advice maybe for you to take note. And remember that I also put some activity over here for your homework. Please do practice problem 10.1. And as usual, Friday is our submission due date uh, before 11:59. And for those who still didn't submit any homeworks that given to you, please do it so. And in next class, next class, not next class, next class is our tutorial on Thursday. Maybe we will discuss a bit on nodal and mesh analysis in general, because you need to revise yourself in order to get familiar with nodal and mesh. And I will maybe the class will be a bit shorter, since some of you guys maybe would like to celebrate your Christmas Eve on 24th. Maybe we're gonna have about 1 hour class. So, all right. Next week, okay, next week, what we try to do is we try to do some extend our knowledge to for AC circuit analysis. We try to have a look at superposition and source transformation. Okay, these two definitely, okay, will be available in your final exam. Definitely, one question will be coming from these two topics. All right. Any questions so far?
No, sir.
Okay. All right. As usual, please turn on your webcam so that I can snap your attendance. Okay. I will snapshot it now. 1, 2, 3. Smile. Okay. Anyway, we see again on Thursday, 11, maybe up until 12. We're gonna have 1 hour class. Okay. Oh, Khairul Naim asked about, can you put the solution for class week before this class? What would we mean class week? Solution? Do you mean a solution for class activity? Ah, okay. I try, but I try, but not promise. I try lah. I try, and I try to put it as soon as possible, because maybe before your final exam lah, before you try to analyze. Sorry, before you try to study for the final exam, I'll try to put every solution in your e-learning so that it's easily for you to revise, do some revision on that. All right. Thank you so much for your attention, and we'll see you again on Thursday. Thank you so much. Assalamualaikum. And oh, before that, please fill out the form, attendance form, before you leave. Okay, I will close the. Uh, Sorry.
I forgot to sign the form for last week. Can I also sign it for today for last week, or I can't?
No, you can't because you missed that one. But it's okay. Please, you just fill out the form for last week because no, you cannot do that. Maybe you can PM me later on. I'll take note on that because
Okay.
I cannot like allow you to do to to fill
Because
out
I was in,
the one that you missed last time.
because I just forgot to sign the form. That was it. I was in the class the whole time.
Yeah, I know. That's why I asked you to PM me later on.
Okay. Thank you, sir.
Okay. Okay. Oh, I may ask about the link. I think this is the link. I mean, 2 weeks. Okay. Thank you so much. Assalamualaikum. See you again next Thursday.
Okay, sir. Thank you, sir.
Thank you.